On September 21, 1942, at Boeing Field in Seattle, Washington, test pilot Eddie Allen advanced the throttles of four Wright R-3350 duplex Cyclone engines. Before him stood a machine that seemed to belong to another era, the Boeing B-29 Superfortress, serial number 41-002. As the bomber's 141-foot wings flexed against the morning light and its 33-ton frame gathered speed, Allen and his crew lifted into history. The aircraft that left the runway that morning was not just another bomber prototype. It was a flying laboratory for technologies that had never coexisted in a single platform. Pressurized crew compartments, remote-controlled gun turrets, centralized fire control computers, and an unprecedented range, over 3,200 miles, 5,150 kilometers, with a full bomb load. Each of these features represented a breakthrough. Together they signaled a fundamental shift in aerial warfare. By May 1943, the first service test aircraft, the B-29, entered evaluation with the U.S. Army Air Forces. Boeing's Wichita, Renton, and Omaha plants began gearing up for mass production. Each B-29 required over 100,000 man-hours to assemble and contained more than 55,000 individual parts. The scale alone dwarfed that of any previous bomber program. To the Germans, who by 1943 were feeling the weight of Allied bombing on their own cities, the B-29 represented something far beyond their current reach. The Heinkel He-177 Greif, Germany's only operational long-range bomber, was plagued by engine fires and unreliable coupling gear. Its combat radius was under 1,000 miles, and it lacked pressurization. Where the He-177 struggled to bomb from 20,000 feet, the B-29 promised routine operations above 30,000 feet, 9,100 meters, at speeds exceeding 350 miles per hour, 560 kilometers per hour. These figures mattered. Altitude meant survival. At 30,000 feet, most German 88mm Flak 36 batteries could not reach an effective kill zone. At 350 miles per hour, the bomber outran standard Luftwaffe interception envelopes. The B-29's altitude and speed rendered entire layers of air defense doctrine obsolete. Inside its sleek, cylindrical fuselage, engineers had created something unprecedented for combat aviation: a fully pressurized environment divided into three sections: forward cockpit, central gunnery tunnel, and aft cabin. A narrow, crawl tunnel over the bomb bays connected the pressurized zones, allowing crew to move mid-flight without exposure to the freezing stratosphere. The environmental system maintained cabin pressure equivalent to 8,000-foot altitude, even while cruising above 30,000. Crew efficiency on 10-hour missions dramatically improved. The defensive architecture was equally radical. Instead of traditional manned turrets protruding from the fuselage, Boeing installed four remotely operated, electrically powered turrets, each housing twin .50 cal Browning M2 machine guns. A tail station carried a fifth battery, 2.50 calories plus a 20mm M2 cannon in later versions. These were controlled by 5 sighting stations linked to a General Electric Central Fire Control (CFC) system, an analog computer that distributed aiming data between stations. Whichever gunner had the best shot took control of the target turret automatically. It was a mechanical brain decades ahead of its time. With it, a B-29 formation could generate overlapping fields of defensive fire at ranges up to 900 yards, accurate enough to hit an incoming fighter traveling 400 miles per hour. For German air defense analysts, still relying on line-of-sight manually aimed guns, this was nothing short of revolutionary. By late 1943, the Allies had poured over $3 billion, equivalent to more than $50 billion today, into the B-29 program, the single most expensive weapons project of World War II, exceeding even the Manhattan Project's early expenditures. It represented not just an aircraft but a systems integration triumph, linking aerodynamics, electronics, metallurgy, and high-temperature engine design into a cohesive combat tool. Every design line of the Superfortress told a story of strategic ambition. Its wing, with a dihedral of 6 degrees, was optimized for high-altitude cruise at Mach 0.58. The Wright R-3350 engines, each a 2,200 horsepower 18-cylinder air-cooled radial, drove 4-bladed, constant-speed propellers nearly 16 feet in diameter. Each power plant consumed around 400 gallons of fuel per hour at military power. At full load, the B-29 could carry up to 20,000 pounds, 9,070 kilograms, of bombs, more than twice that of the B-17 Flying Fortress. Even before the aircraft entered combat, its very specifications were reaching German intelligence units through aerial observation, Allied press releases and intercepted radio chatter. At the Reichsluftfahrtministerium, RLM. In Berlin, engineers and analysts under the Technisches Amt began compiling profiles of this new bomber. They estimated its range, altitude, and payload, numbers that exceeded what even the most ambitious German prototypes, such as the Messerschmitt Me-264 America bomber, could achieve. To German planners it posed an existential challenge. If the Allies could mass-produce such machines, Germany's remaining defenses, already overstretched across the Reich, would face a bomber capable of striking from beyond fighter range, above flak ceilings, and with precision guided by advanced analog computation. But in 1942-43, few German officers yet grasped what that meant. They saw the B-29 as another heavy bomber, not a revolution. Only the engineers, those parsing the specifications line by line, understood that something irreversible had happened. The gap between the Axis and Allied aviation industries was no longer measured in horsepower or caliber. It was measured in systems integration, in the seamless coordination of aerodynamics, electronics, and industrial scale. When the first B-29 combat units, the 58th Bombardment Wing, began deploying to India and China in April 1944, the blueprint of future air warfare had already been written. German intelligence knew it, even if they couldn't yet see it. And when, in 1945, captured engineers finally studied a full B-29 blueprint, the verdict was immediate. This aircraft could rule the skies, not just by power but by architecture. By early 1943, deep inside the Reichsluftfahrtministerium, RLM, in Berlin, reports began filtering in about a new American bomber under accelerated development, an aircraft so large and advanced it bordered on implausible. The Technisches Amt, the Luftwaffe's technical department, assigned engineers from its GL/CE2, aircraft evaluation, section to track every trace of information coming out of the United States and Britain about this mysterious superfortress. At first, these fragments came through indirect channels: Allied newsreels, neutral press, and espionage intercepts. German attaches in neutral Switzerland and Sweden compiled translated clippings from aviation magazines describing Boeing's new long-range heavy bomber. They noted repeated mentions of pressurization, remote control armament, and extraordinary range, concepts that suggested an aircraft operating in an entirely different design paradigm. The Luftwaffe's intelligence arm, Abteilung 5, Technische Aufklärung, cross-referenced these open sources with technical data from captured American aircraft. Each clue was measured against German design limits. When word spread that the bomber's Wright R-3350 duplex Cyclone engines produced over 2,200 horsepower each, analysts were alarmed. No German airframe in mass production carried that kind of sustained power, especially not at 30,000 feet. By mid-1943, Allied reconnaissance flights over Europe were revealing new American aircraft silhouettes at distant bases. German analysts misidentified some as experimental variants of the B-17, until aerial photographs of Marietta, Georgia and Wichita, Kansas plants, taken by diplomatic attaches before America's entry into the war, were re-examined. The construction scale dwarfed anything in Germany. Where Heinkel and Junkers factories turned out hundreds of aircraft per month, Boeing's facilities were expanding toward thousands. The message was clear. Industrial capacity could now produce a machine as sophisticated as the B-29 in numbers that could overwhelm any defense network. Still, what truly activated German technical intelligence was not press coverage or rumor, it was field evidence. In December 1943, intercepted USAF logistics manifests referenced the transport of B-29 fuselage sections, by rail through Kansas and California. Analysts concluded that the aircraft had entered pre-production. Luftwaffe signal intercept units under Oberstleutnant Erich Kulenthal relayed these findings to Berlin. The Technisches Amt convened a closed technical review in January 1944, attended by representatives from Messerschmitt, Junkers, Heinkel, and Dornier. At that meeting, engineers examined every available metric: projected ceiling 30,000 feet, combat radius 2,700 miles, bomb load 20,000 pounds, and speed 350 miles per hour. Each number was charted against German aircraft in service. The comparison was stark. The He-177A5 could reach 27,000 feet only when lightly loaded, with an effective range of 900 miles. The Ju-188 and Ju-217 were medium bombers by every measure. No German machine combined altitude, range, and payload the way the B-29 reportedly did. Technical officers in attendance recorded the verdict in internal memoranda. If operational, this bomber surpasses all present defensive altitude bands and renders 8.8 centimeters flak 36 ineffective above 9 kilometers. Another noted, at 10 kilometers interception requires pressurized fighters with ceiling above 12 kilometers. None in current series production. In April 1944, the U.S. deliberately flew a YB-29 prototype to Britain, serial number 41 to 36954, nicknamed Hobo Queen. It was displayed at several RAF bases to test logistics for European deployment. The aircraft's silhouette was unmistakable, an immense mid-wing bomber with high aspect ratio tailplane and long nacelles. Luftwaffe reconnaissance units in northern France photographed it. Within days, German analysts in Paris confirmed that the machine was real, and far larger than any previous American bomber stationed in Europe. The presence of the Hobo Queen ignited panic within Germany's Reichsverteidigung, Home Defense Command. Air Marshal Hugo Spurl, commanding Luftflotte 3, requested detailed assessments from the Oberkommando der Luftwaffe, OKL. If the Americans intended to bring such bombers into the European theater, existing fighter defenses, organized around Bf-109G and Fw-190A groups, would be ineffective at the required altitudes. That summer, the Luftwaffe Führungsstab issued a directive to the aircraft industry. Explore high-altitude fighter concepts with service ceilings above 40,000 feet. This led to renewed interest in the Messerschmitt Me-155, the Junkers EF-127, and especially the Me-262 jet interceptor. The jet's Jumo 004B engines promised the climb rate and speed necessary to reach bombers like the B-29. What had begun as an intelligence report was now shaping aircraft development policy. At the same time, the Reichsforschungsrat, Reich Research Council, instructed German engineers to gather all technical data on Allied bombers recovered from crashes. Each piece of American equipment, oxygen regulators, bomb bay controls, electrical systems, was catalogued and reverse engineered. Engineers understood that if they could obtain even fragments of a B-29, the knowledge would alter German bomber design for years. But access to a real B-29 remained impossible. The aircraft were deployed exclusively in the Pacific theater, far from German reach. So the Luftwaffe's analysts worked from photographs, intelligence estimates, and physics. Using aerodynamics tables, they calculated lift coefficients and power-to-weight ratios from known dimensions. The results were sobering. At cruise, the B-29 achieved a lift-to-drag ratio of approximately 18:1, superior even to Germany's most efficient gliders. By late 1944, as the Allies advanced toward the Rhine, German engineers within the Istel-Recklen Test Center compiled a classified document titled Bewertung der Boeing Superfortress, Evaluation of the Boeing Superfortress. The report summarized what was now undeniable. This aircraft introduces a total system combining high-altitude pressurization, automated defensive fire control, and unprecedented range. No equivalent exists within the Reich. Countermeasures must include jet propulsion and radar-guided flak. In parallel, the Technisches Amt circulated a new technical intelligence directive. B-29 type design must define future bomber architecture. It marked a turning point, the moment when German intelligence shifted from disbelief to strategic analysis. For the first time, they accepted that a technological generation gap existed. Across Germany's aircraft firms, engineers began sketching theoretical counters. Faster jets, higher-flying reconnaissance planes, larger four-engine bombers. But while they were drawing, the war was collapsing around them. Fuel shortages crippled testing programs, and Allied raids burned the very factories trying to respond. Still, within the cold offices of Recklen and Oberpfaffenhofen, men like Heinrich Hertel, Ernst Heinkel, and Willy Messerschmitt studied the fragmentary blueprints and photos. They were not just studying an aircraft. They were witnessing the future of air warfare, one in which the B-29, whether or not it flew over Europe, had already redefined the possible. By January 1945, deep in the cold offices of Istel-Recklen, Germany's principal flight test center, engineers unrolled large-format photographs and intelligence sketches on a long oak table. The title on the folder read, Boeing B-29 Superfortress, Technische Bewertung. It was the most detailed technical reconstruction German analysts ever produced of the American bomber. They had no captured aircraft, no intact wreckage. Every data point had been reverse-engineered from reconnaissance images, Allied press descriptions, and the meticulous performance reports emerging from Luftwaffe listening stations. Yet, line by line, they assembled a remarkably accurate portrait of what the B-29 truly was, and what it represented. The first section dealt with aerodynamics. Using estimated dimensions, wingspan 141 feet 3 inches, 43.05 meters, length 99 feet 0 inches, 30.18 meters, wing area 1,736 square feet, 161.3 square meters. Engineers calculated a wing loading of 77 pounds per square foot at maximum takeoff weight. That figure astonished them. No German bomber came close. The Heinkel He-177 carried 65 pounds per square foot, and even the planned Me-264 America bomber projected only 70 pounds per square foot. The higher wing loading implied advanced high-lift airfoils and superior structural integrity. It meant the B-29 could fly faster and higher without sacrificing stability. The next section analyzed propulsion. Reports indicated that the bomber used 4 Wright R3350-23 duplex Cyclone engines, each delivering 2,200 horsepower at takeoff, driving Curtiss electric constant-speed propellers of 16 feet 7 inches diameter. Combined, that produced nearly 8,800 horsepower, a figure that forced German analysts to recalculate drag curves. They determined that the aircraft's maximum speed of 357 miles per hour, 575 kilometers per hour, at 30,000 feet aligned perfectly with that power output. But what truly captured their attention was the supercharging system. Each engine was equipped with a 2-stage turbo supercharger, using exhaust gases to maintain manifold pressure at high altitudes. German engines, like the Jumo 213E and BMW 801D, used mechanical superchargers, but no comparable 4-engine turbo installation had been operational. The B-29's turbo supercharging allowed it to sustain high power at 31,000 feet, where Luftwaffe piston fighters struggled for lift. Then came the pressurization study. Recklin's engineers had long experimented with sealed cabins for high-altitude reconnaissance aircraft like the Ju-86P, but these systems were fragile and maintenance-intensive. The B-29, however, employed a dual-compartment pressurization system, separated by bomb bays and connected through a pressurized tunnel. The forward section housed the pilots, bombardier, and navigator. The aft section contained gunners and the radar operator. Using airscoop diagrams drawn from photographs, German engineers estimated a pressure differential of 6.5 psi, enough to simulate an 8,000-foot cabin altitude while flying at 30,000 feet in practice. This meant crews could operate without oxygen masks for 10-hour missions. A decisive factor in endurance and accuracy, one German engineer wrote in the report margins. In contrast, Luftwaffe bomber crews operating above 20,000 feet wore heavy pressure suits and oxygen masks that fogged, froze, or failed during long sorties. The section on defensive armament was perhaps the most shocking. Allied reports and intercepted maintenance manuals confirmed that the B-29 carried 5 remotely operated turrets, each armed with 2 Browning and /M 2.50 caliber machine guns, with the tail position optionally fitted with a 20mm M2 cannon. Control of these guns came through a General Electric Central Fire Control (CFC) system composed of analog gyroscopic computers and periscopic sighting stations. To the German mind, this was unprecedented. They were accustomed to direct mechanical linkages, turrets aimed by hand, firing arcs limited by the gunner's endurance. The idea that a single gunner could, through a computing sight, control multiple turrets automatically was a revelation. The CFC system's analog logic circuits, using synchros, amplitudes, and electric servos, computed target lead, range, and deflection in real time. At Rechlin, an engineer named Dr. Richard Voigt noted, "The B-29's gunnery represents a leap beyond mechanical coordination. It is the application of computation to air defense." He underlined the word computation. Germany's own analog systems, such as the Lot 7K bomb sight and EZ-42 gyroscopic sight, were advanced but limited to single functions. The Americans had networked 5 turrets and 5 gunners into a distributed analog control system, effectively the first digital network in aviation history. German analysts calculated firing coverage. Each turret could traverse 360 degrees, with elevation arcs from -10 degrees to +90 degrees. When integrated across 5 stations, this produced continuous defensive coverage for the entire airframe. The computed field of fire left no blind spot larger than 15 degrees, compared to 45 degrees gaps on the He-177. No massed attack in line astern could succeed, the report concluded. Only high-speed frontal assaults, exceeding 800 km per hour, may disrupt fire solution. That realization triggered a doctrinal panic. Luftwaffe interceptors like the Bf-109G6 or FW-190A8 could barely reach 9,500 meters, and even then their speed advantage was minimal. At that altitude, oxygen flow faltered, engine performance dropped, and formation attacks became chaotic. The B-29's effective sealing rendered those tactics obsolete. Finally, German engineers examined payload and range. The bomber's two bomb bays could carry up to 20,000 pounds, 9,070 kilograms, of ordnance internally, roughly equivalent to a full load of 40 by 500 pounds bombs or a single 10,000 pounds high-capacity bomb. Internal fuel capacity exceeded 7,000 gallons, 26,500 liters, feeding via cross-linked, self-sealing tanks. Estimated operational radius, 2,900 miles, 4,670 kilometers, with a 1-ton payload. These numbers dwarf German capability. The Me-264, still in prototype, could barely reach 2,000 miles with half that payload. The Americans have achieved the long-range bomber we only drew, noted one memo to the RLM in February 1945. By March, when fragments of captured B-29 wreckage from the Pacific reached German engineers via Japanese liaison channels, the verdict was already settled. A translated Japanese report from Manchuria, based on a B-29 crash near Anshan in December 1944, confirmed the German calculations almost to the decimal. Recklin's engineers added a final page to their analysis, Folgerungen für zukünftige Flugzeugtypen, implications for future aircraft types. It summarized the essence of their discovery in 4 lines. Pressurization indispensable for sustained altitude above 9 kilometers. Turbo-supercharging mandatory for engine performance beyond 8 kilometers. Automated fire control now essential to bomber defense. System integration, the new measure of air power. For the Luftwaffe, this was the moment of recognition. The B-29 was not just a bomber, it was a prototype of a new kind of warfare, one that fused electronics, aerodynamics, and endurance into a single strategic weapon. But recognition came too late. The factories that could have built its German counterpart were already in ruins. By spring 1944, Germany's air defense network was stretched to its limits. The skies above Hamburg, Munich, and the Ruhr burned nightly with the contrails and searchlights of the Allied bombing offensive. Yet amid that chaos, the Luftwaffe's technical analysts faced a revelation even more unsettling than the bombing itself. The B-29 superfortress had redefined the very physics of strategic bombing. In a confidential briefing at Karenhall, Hermann Göring's estate northeast of Berlin, senior Luftwaffe officers gathered in late April. On the long conference table lay a dossier marked U.S. Heavy Bomber, Type B-29, compiled from Luftwaffe and RLM technical intelligence. It described a machine capable of cruising above 30,000 feet, faster than the best German interceptors at that altitude, and carrying a bomb load that could level an industrial district in one sortie. General der Jagdflieger Adolf Galland, commander of all fighter forces, skimmed the document and shook his head. "If they bring this here," he said quietly, "we will not reach them." The statement was neither dramatic nor defeatist, it was technical fact. For the Luftwaffe, doctrine and technology had always moved hand in hand, but now doctrine lagged behind. Since 1940, German Reichsverteidigung, home defense. Doctrine relied on the assumption that bombers operated below 26,000 feet and under 300 miles per hour. Interception patterns, radar calibration, and flak zoning all conformed to that model. The B-29 shattered it. At 30,000 feet, even the vaunted 88mm Flak 36 could only engage for a few seconds before projectiles lost altitude. The Luftwaffe's early warning radar, Freya and Würzburg D, lost precision beyond 10 kilometers. The air defense map, the mathematical backbone of Germany's skies, was now obsolete. To adapt, the Luftwaffe initiated Project Hohenjager, High-Altitude Fighter Project, in May 1944. Its objective: develop interceptors capable of sustained operations above 12 kilometers, 39,000 feet. Several aircraft were considered. Messerschmitt Me-155B, a naval fighter design repurposed for high altitude, intended ceiling 49,000 feet. Heinkel He-162H, a jet-powered interceptor with extended wings and GM-1 nitrous oxide boost. Focke-Wulf Ta-152H-1, a stretched, pressurized derivative of the FW-190 with a Jumo 213E engine and two-stage supercharger. Of these, only the Ta-152H reached limited production. Around 47 aircraft delivered between January and April 1945. In test climbs at Rechlin, it reached 14,800 meters, 48,500 feet, matching B-29 altitude. But by then the bomber threat over Germany came not from B-29s, but from B-17s and Lancasters, and even so, fuel shortages grounded most operational squadrons. Still, the concept was sound. The Ta-152H, with its pressurized cockpit and high-aspect wings, was Germany's first real attempt to counter a B-29 class threat. Had it appeared a year earlier in numbers, it might have restored parity in altitude warfare. Meanwhile, engineers at Messerschmitt AG examined how to replicate the B-29 system's integration. The idea of an America bomber resurfaced, this time grounded in data from the captured intelligence dossier. On July 10, 1944, a memo from Messerschmitt's Augsburg design office proposed an aircraft, with pressurized fuselage, remote-controlled defensive armament, and range exceeding 10,000 kilometers. That memo referenced the Me-264 already built in prototype form, and the even more ambitious Ju-390. The Me-264 V1, first flown in December 1942, was resurrected for evaluation. Powered by four Jumo 211J engines producing 1,340 horsepower each, it was underpowered from the start. But its airframe, long fuselage, high wing, streamlined nose, suggested potential for modernization. Engineers proposed fitting DB603A engines, 1,750 horsepower, a pressurized cockpit and a simplified remote turret system inspired by B-29 analysis. None of this materialized. Germany's aluminum output had collapsed to below 60,000 tons per month, barely enough for fighter production. Parallel to these technical debates, Luftwaffe doctrine was being rewritten on paper faster than it could be tested in the air. A July 1944 directive from Generaloberst Hans Gestionek's staff, issued posthumously after his suicide the previous year, outlined a new model: decentralized radar control, jet interception and high-altitude flak belts. The 8.8 cm Flak 41 and 12.8 cm Flak 40 were pushed into production, capable of reaching 14 km ceiling. But even these massive guns required radar prediction accuracy Germany could no longer sustain under bombardment. In short, the Luftwaffe understood the tactical implications of the B-29, but not how to meet them. Its entire warfighting system, from radar to flak, from fighter climb profiles to mission planning, had been built for a lower sky. The Americans had simply moved the war upward. There were internal critics. Dr. Walter Dornberger, head of Germany's long-range weapons development, argued that the future lay not in intercepting bombers but in preemptively destroying their bases, via long-range missiles. He cited the B-29's projected range and payload as proof that geography had ceased to matter. Whoever commands the stratosphere, he wrote, commands the continent. His team's A9/A10 rocket designs, a two-stage intercontinental missile, were a direct theoretical response to the B-29's reach. But it was too late for theory. On June 15, 1944, as the first B-29 struck Yoda, Japan, German observers attached to Japanese intelligence watched in disbelief. The bombers had flown over 3,200 miles round-trip from Chengdu, China, to hit a steelworks with minimal losses. A bomber that could fly from India to Manchuria was no longer a tactical aircraft. It was a strategic instrument. The Oberkommando der Wehrmacht (OKW) received the mission reports via Tokyo liaison within 10 days. Their analysis, dated June 25, 1944, concluded tersely, if this machine were deployed from British bases, our industrial heartland would be untenable. From that moment, German design philosophy pivoted, on paper, toward system-level innovation. Remote fire control, pressurization, high-altitude engines, and integrated electronics became the new benchmarks. But in the ruins of Regensburg, Dessau, and Bernburg, the factories capable of realizing them were already ash. Innovation had defeated doctrine. The B-29 had not merely outflown the Luftwaffe, it had outthought it. The B-29's reputation had already crossed oceans by mid-1944. Long before a single superfortress appeared over Japan, fragments of intelligence filtered into Europe through the Japanese-German technical exchange network known as Yanagi missions. Operated via long-range submarines, I-8, I-29, and U-511, the system ferried blueprints, alloys and technical reports between Axis partners. Among the crates of radar parts and aircraft optics came documents that would set German engineers ablaze with curiosity: partial schematics of Boeing's new bomber. The most significant cache arrived in July 1944, when the Japanese submarine I-29 reached Singapore after a perilous 12,000-mile voyage from Kure. Aboard were not just intelligence officers but 3 engineers from the Nakajima Hikoki KK, carrying microfilm rolls of U.S. aircraft captured or analyzed in the Pacific. These included reconnaissance sketches of the B-29 superfortress, sourced from downed or photographed examples over China. The Kriegsmarine transferred I-29's cargo to U-864, a Type IXD-2 submarine under Korvettenkapitän Ralph Reimar Wolfram, for the return journey to Europe. The U-864 departed Kiel in December 1944 with over 67 tons of mercury and an estimated 2 trunks of microfilm documents bound for Japan on the return leg, proof of the two-way flow of war science. But she never completed the voyage. On February 9, 1945, off Bergen, Norway, she was intercepted and sunk by HMS Venturer, the only known instance of one submarine sinking another while both were submerged. Her loss likely ended any remaining exchange of B-29 data to Germany. Yet, by then, fragments of the B-29's design had already reached Dessau and Augsburg. The Reichsluftfahrtministerium, RLM, distributed what it called Evaluation Report 234/44, Amerikanischer Fernbomber Typ B-29. This 42-page dossier, compiled from intercepted radio descriptions, Swedish trade intelligence and Japanese source sketches, was circulated to the research divisions of Junkers, Messerschmitt and Heinkel. Its details were incomplete but startlingly modern. The B-29 used electrically powered, remotely controlled gun turrets, each coordinated by analog computing sites, the General Electric Central Fire Control System. The turrets used twin .50 cal M2 Browning machine guns and in the tail, an additional 20 mm cannon. Defensive coordination was done through a central gunner, a concept no Luftwaffe bomber employed. To the German engineers at Junkers Flugzeug und Motorenwerk AG, it was an alien philosophy. Their own Ju-290 and Ju-390 relied on manual turrets and direct sighting, each gunner isolated. The B-29's centralized system reduced drag, cut crew size, and increased situational awareness. The Germans saw in it the fusion of electronics and aerodynamics, a domain they had explored but never mastered under wartime constraints. At Dessau, chief designer Ernst Zindel ordered his engineers to create a technical cross-study. Their findings, preserved in post-war archives, read like an autopsy of ambition. One engineer, Dr. Hans Mach, noted, "The American system integrates gunnery, flight control, and pressurization into one concept of warfare. Each is not separate but systemic." The Luftwaffe's technical branch, Technisches AMTGL/CE2, responded by initiating the Fernbomberuntersuchung long-range bomber study in late 1944. The project merged existing German designs under a new goal, an aircraft capable of 10,000 km range, 8,000 kg bomb load, and operation at 12 km altitude. 3 designs were compared. Junkers Ju-390A1, 6-engine derivative of the Ju-290, wingspan 165 feet, max range 9,700 km. Messerschmitt Me-264B, 4-engine high-speed bomber, wingspan 141 feet, projected range 15,000 km. Heinkel He-277, unbuilt heavy bomber concept, designed to carry 7 tons of bombs at 600 km per hour. When placed beside the B-29 specifications, 141-foot wingspan, 32,000-foot ceiling, 350 miles per hour cruise, 9,000 km range, it was clear, Germany had concepts, but no production reality. To close that gap, RLM authorized a series of component studies specifically modeled on B-29 features. Pressurization. Junkers built an experimental cabin mock-up using reinforced duralumin at Rechlin, but lacked reliable rubberized seals. Cabin tests failed at 0.35 atm differential pressure. Remote fire control. Siemens and Halske attempted to replicate the analog computation mechanism using their Loth 7K bombsight gyros. The prototype turret jammed after 45 seconds of operation due to overheating servos. Centralized turret coordination. Telefunken engineers proposed adapting FUG 240 Berlin radar for fire control, but its magnetron components were too scarce to spare. Each trial ended not in failure of design but of resources. Germany could not mass-produce the precision motors or vacuum tube systems the B-29 required. The same scarcity that crippled the Me-262 jet program now doomed the reverse engineering effort. Nevertheless, the German fascination deepened. At Oberammergau, where the Luftwaffe maintained its Technische Schule der Luftnachrichtentruppe, Air Signals Technical School, captured Allied gun camera footage of B-29s was studied frame by frame. Analysts recorded flight altitudes of 9,000 to 10,500 m, bomb bay configurations, and even propeller pitch patterns to infer engine torque characteristics. By February 1945, Germany's war machine was collapsing, but inside the reinforced tunnels of the Mittelwerk complex near Nordhausen, the engineers of Mittelbau-Dora still discussed how to adapt B-29 design logic to the upcoming A9/A10 intercontinental rocket. In their notes, the bomber systems became reference points for integration, how to fuse avionics, control systems and crew survival into one closed environment. After Germany's surrender on May 8, 1945, Allied intelligence teams scoured these facilities. The U.S. Army Air Force's Operation Lusty, Luftwaffe Secret Technology, retrieved surviving RLM documents, including the Fernbomberuntersuchung. The irony was complete: American engineers studying German reports analyzing an American bomber. In the final accounting, Germany never built a working B-29 equivalent, but the process of trying to understand it shifted their engineering philosophy from craft to systems. It was the beginning of what the U.S. would later call aerospace engineering. When the guns fell silent in May 1945, the race to capture technology began. While American teams swept through Bavaria and Saxony gathering jets, rockets and radar, the Soviet Union focused on one target above all: the B-29 Superfortress. The bomber had never flown a combat mission over Europe, but by 1945 its myth preceded it: a weapon that could cross oceans, bomb at 30,000 feet and return home unscathed. For the Soviets, who possessed nothing comparable, the B-29 was not just a marvel, it was a template for survival in the coming nuclear age. The opportunity arrived by accident. On July 29, 1944, 3 B-29s from the U.S. 58th Bomb Wing, Ramp Tramp, General H. Arnold Special, and Ding Hao, were forced to land in Vladivostok, Soviet territory, after bombing Japan from Chengdu, China. The Soviet Union, still neutral in the Pacific War, interned the aircraft and crews as per international law. But while the airmen were quietly repatriated via Iran, the aircraft were not returned. Instead, they were meticulously dismantled under the supervision of Andrei Tupolev, chief designer of the TSAGI, Central Aerohydrodynamic Institute. The order came directly from Stalin in August 1944, copy it exactly, down to the last rivet. The B-29s were trucked to Moscow's Kodinka airfield, then to Plant No. 156, Tupolev's main design bureau. The three airframes, identified as 42-6356, 42-6365, and 42-6358, became the genetic code for what would soon be called the Tupolev Tu-4. Reverse engineering at industrial scale. The Soviet challenge was monumental. Unlike Germany, whose engineers had only intelligence reports and fragments, the Soviets had three complete aircraft, but not the manufacturing ecosystem behind them. The B-29 was an industrial organism of over 55,000 individual parts, many built to tolerances and alloys unknown in Soviet metallurgy. Over 900 factories across the USSR were mobilized for the duplication effort. By late 1945, the Soviet Air Force (VVS) had disassembled one B-29 into 105,000 individual drawings, each reproduced by hand in metric measurements. Where the Americans used imperial bolts, a quarter inch, the Soviets substituted 6 mm. Where the US used high-tensile aluminum alloy 75 ST6, the Soviets adapted with duralumin V95, close but not identical. Every deviation had to be documented. When inspectors reported a 0.4 mm variance in wing spar thickness, Tupolev insisted the design be recalculated, not guessed. The result was astonishing: a near-perfect clone of the B-29, known initially as Aircraft 64. By May 1947, just 2 years after Germany's defeat, the first Tu-4 rolled out of Plant No. 22 at Kazan. From a distance, it was indistinguishable from the Boeing original, save for red stars on the tail. Its specifications mirrored the B-29's. Range, 5,600 kilometers. Ceiling, 10,500 m. Speed, 558 kilometers per hour. Bomb load, 12,000 kilograms. The Soviet engineers had even replicated the General Electric Central Fire Control System, renaming it the Bu-13. Though less precise, it operated on the same principle of gyroscopic lead calculation and remote-controlled turrets. Strategic consequences. The Tu-4 entered service in 1949, the same year the Soviets detonated their first atomic bomb at Semipalatinsk. For the first time, Moscow possessed a delivery vehicle capable of reaching London, Paris, or even Chicago, a direct inheritance from an American bomber that had crash-landed in Siberia 5 years earlier. In a geopolitical sense, the Tu-4's creation was the hinge of the early Cold War. It provided the USSR with an immediate nuclear deterrent and forced the United States to accelerate development of jet-powered long-range bombers, the B-47 Stratojet and later B-52 Stratofortress. The Soviets built 847 Tu-4s between 1947 and 1953, forming the backbone of long-range aviation (DA). They were used not only for nuclear readiness but as testbeds for radar, electronic warfare, and in-flight refueling, each a concept learned from the B-29's integrated systems. Meanwhile, in post-war Germany, surviving Luftwaffe engineers like Kurt Tank, Ernst Heinkel, and Willy Messerschmitt were astonished by Soviet progress. In interviews conducted by Allied occupation authorities in 1946, several admitted that the B-29 replication surpassed anything Germany had achieved. They did what we could not, Tank noted, because they had the machine complete. Ironically, fragments of German wartime research, collected under Operation Osoaviakim in October 1946, were now feeding back into Soviet bomber development. Hundreds of German engineers, including experts from Junkers and Messerschmitt, were forcibly relocated to Podberezhny and Zhukovsky, where they joined the Tu-4 derivative program. The cross-pollination was direct. German systems knowledge merged with American hardware through Soviet hands. By 1950, modified Tu-4s were conducting radar reconnaissance flights along the Arctic Circle, shadowing U.S. bomber routes. American intelligence identified them as Type 4, unable at first to believe the Soviets had reverse-engineered an entire B-29 fleet in just 4 years. Legacy of the copy. The Tu-4 symbolized more than imitation. It was the formal birth of Soviet strategic aviation. From it evolved the Tu-16, Tu-95, and eventually the Tu-160, each expanding on the principles of systems integration first observed in Boeing's wartime design. When Western analysts reviewed captured German reports on the B-29 from 1944 and compared them to Soviet documents from 1947, the through line was clear. The Germans had understood what the B-29 represented, high-altitude, high-integration warfare, but lacked the resources to act. The Soviets, inheriting both the insight and the wreckage, had turned observation into production. In the war's final calculus, Germany had studied the B-29, the Soviets industrialized it. The result redrew the map of global air power. A bomber that had once targeted Tokyo now, through its clone, threatened Washington. And all of it began with 3 damaged aircraft that landed by chance on Soviet soil. By the dawn of 1946, as nations dismantled their wartime industries, air power theory was being rewritten in hangars and briefing rooms across 3 continents. The B-29 Superfortress had not just ended a war, it had exposed a new equation of dominance. Altitude plus range plus systems integration equals control of the battle space. Its impact on design philosophy was immediate, measurable, and global. For the United States Army Air Forces (USAF), the B-29 had validated the concept of strategic autonomy. Unlike its predecessors, the B-17 Flying Fortress or the B-24 Liberator, the Superfortress could project force without reliance on forward bases or escort fighters. On August 6 and 9, 1945, the atomic strikes on Hiroshima and Nagasaki proved that a single aircraft, flying 1,500 miles from Tinian Island, could end a war. The implications reverberated far beyond the Pacific. Within 6 months, the U.S. initiated Project RAND, Research and Development, tasked with predicting how future wars would be fought using high-altitude, long-range bombers and emerging jet propulsion. RAND's first classified report in May 1946, titled Preliminary Design of an Experimental World-Circling Spaceship, directly cited lessons learned from the B-29's flight endurance, fuel management, and pressurized crew systems. In other words, the leap from superfortress to spaceflight was a straight line. Systems integration as doctrine. Before 1944, aircraft were still collections of subsystems. Engines, guns, radios, operating semi-independently. The B-29 changed that. Every system on board was designed to communicate. Pressurization linked to electrical control, gunnery linked to radar tracking, navigation integrated with flight stability. This total systems approach became the template for post-war aerospace design. The Central Fire Control System, CFCS, alone embodied this revolution. Each B-29 turret was connected to a network of analog computing units, essentially early mechanical processors, that calculated firing angles based on target speed, distance, and relative position. The system could engage multiple fighters simultaneously with coordinated fire, using just 5 gunners for a defensive sphere covering 360 degrees. This principle, distributed coordinated computation, would later reappear in both jet fighters' fire control radars and ICBM guidance systems. In retrospect, the CFCS was not merely a weapon, it was the prototype for digital warfare. German engineers who studied the captured blueprints at Rechlin recognized this immediately. Their 1944 report concluded, "The American bomber is not an airframe carrying weapons. It is a system whose weapons are the airframe." That sentence would become prophetic. Impact on jet bomber development. The post-war bomber race unfolded directly from the B-29's architecture. The United States' next-generation designs, B-50, B-47, and eventually B-52, retained the Superfortress's core geometry: shoulder-mounted wings, tricycle landing gear, pressurized fuselage, and centralized command compartment. The B-50 Superfortress, introduced in 1947, was essentially an upgraded B-29 with more powerful R-4360 Wasp major engines and structural reinforcements. It set the non-stop world flight record in 1949, circling the globe in 94 hours with in-flight refueling, a concept studied during B-29 operations. Then came the B-47 Stratojet, first flown December 17, 1947. Its swept wings and jet propulsion marked the shift from piston to turbine power, but its operational philosophy, high altitude, centralized systems, electronic navigation, was pure B-29 DNA. Boeing engineers often referred to the B-47 as the B-29 rewritten in jet. On the Soviet side, the Tu-16 Badger and Tu-95 Bear traced similar lineage. Both borrowed structural and system logic from the Tu-4 clone, itself derived from the B-29. The chain of influence was technical, not ideological, proof that engineering progress transcends politics. Even Britain's Avro Lincoln and later Vulcan bore echoes of the American machine they had never flown. By the 1950s, every strategic bomber in the world shared the B-29's genetic framework: high-altitude pressurization, centralized electronics, and modular crew stations. Doctrine in transition. Strategic bombing doctrine also evolved. The B-29 had demonstrated that wars could be won not by attrition but by industrial paralysis. Its campaign over Japan, 1.5 million tons of bombs dropped between November 1944 and August 1945, burned 40% of Japan's urban area and destroyed 66 cities. The lesson was stark: control of altitude equaled control of outcome. The U.S. Air Force, established as a separate branch in September 1947, codified these principles into Strategic Air Command (SAC) doctrine under General Curtis LeMay. LeMay, who had overseen the B-29 fire raids, translated wartime tactics into peacetime deterrence: constant readiness, intercontinental reach, and absolute precision. The B-29 thus became not just a bomber but the blueprint for a strategic mindset that would govern nuclear policy for decades. Technological ripples. Beyond doctrine, the B-29 catalyzed innovations that shaped the entire jet age. Pressurization technology, adapted for commercial aviation, leading directly to the Boeing 377 Stratocruiser and later the 707 jetliner. High-octane fuel management. Lessons from its 12-tank system informed the design of long-range reconnaissance aircraft such as the U-2. Analog to digital transition. The bomber's computing gun sights evolved into the first transistorized fire control systems by 1952. By the early 1950s, the B-29's descendants were orbiting the Earth in concept form. Missiles, satellites, and reconnaissance drones all owed part of their system's logic to Boeing's wartime laboratory. Even the Soviets acknowledged this continuity. In a 1955 internal VVS report on bomber modernization, engineers wrote, "Every line of our 2 series traces back to the American B-29. It taught us how to think of the airplane as a weapon system, not a vehicle." Conclusion of a revolution. From German analysts sketching diagrams in 1944, to Soviet engineers copying rivets in 1945, to American designers drawing swept wings in 1947, the B-29 had become the keystone in aviation's transition from propeller warfare to the jet age. Its greatest lesson was not technological but philosophical: integration equals dominance. No aircraft before or since so thoroughly defined the parameters of its era. The Superfortress was both an ending and a beginning, the closing act of mechanical war and the opening scene of electronic strategy. At dawn on June 25, 1950, the first B-29s of the 19th and 22nd Bomb Groups lifted off from Kadena Air Base, Okinawa, bound for targets in North Korea. It had been just 5 years since the end of World War II, Yet the aircraft that had once destroyed Tokyo was again the centerpiece of global warfare. This time it was not introducing atomic fire, but defining the boundaries of Cold War power. The B-29's reappearance in combat during the Korean War, 1950 to 1953, proved how enduring its technological foundations were. The aircraft that once dominated piston-engine skies now faced the jet-powered MiG-15, a product of Soviet engineering that traced its design lineage to both German and captured Allied research. The matchup was historic, the first confrontation between wartime innovation and the jet revolution it had inspired. At 31,000 feet, over the Yalu River, B-29 formations met squadrons of MiG-15s flown by Soviet pilots masquerading as North Koreans. The results were sobering. Between April and October 1951, U.S. bomber losses forced a complete doctrinal shift. What had once been an untouchable machine was now vulnerable. In response, the U.S. Air Force converted B-29 operations to night-only raids, ceding daylight skies to the faster jets. But even in retreat, the superfortress fulfilled its role as the teacher of modern air power. The lessons of Korea, speed, radar bombing, electronic countermeasures, directly informed the design of the B-47 Stratojet and B-52 Stratofortress, both inheritors of its structural DNA and operational logic. Blueprints into doctrine. By the mid-1950s, the B-29 had transcended hardware. It had become a doctrinal cornerstone. Every major air force, American, British, Soviet, now organized its strategic thinking around what the B-29 had first demonstrated, that control of range and altitude determined the reach of policy itself. In Washington, the National Security Council Report 68, NSC 68, finalized in April 1950, codified this belief. It argued that America's security depended on the ability to deliver overwhelming force across continents, by air and if necessary from orbit. The B-29's technological lineage thus formed the core of Cold War deterrence. Long-range bombers circling silently over oceans, visible proof of industrial supremacy. At Strategic Air Command, SAC, headquarters in Offutt Air Force Base, Nebraska, General Curtis LeMay established a new operational rhythm: 24-hour airborne readiness, systematic refueling and nuclear-tipped alert missions. Many of his senior crews were B-29 veterans. Their combat discipline, tight formations, precision navigation, redundant systems, became the human extension of the superfortress's engineering logic. By 1957, LeMay commanded over 2,500 strategic bombers, including 744 B-52s, a direct descendant of Boeing's wartime masterpiece. The lineage was unmistakable, for engines had become 8, propellers had become turbojets, but the underlying philosophy, pressurization, range, coordination, remained identical. Global echoes. The B-29's influence extended far beyond American doctrine. In the Soviet Union, the Tu-4 continued production until 1952, serving as a technological stepping stone toward the Tu-16 Badger and Tu-95 Bear. The Tu-95, first flown in 1952, would remain in service for over 7 decades, a living echo of the B-29's structure and design philosophy. China too entered the lineage. In 1953, the Soviet Union transferred Tu-4s to the People's Liberation Army Air Force, PLAF, where they were later converted for reconnaissance, electronic warfare and even airborne radar roles. By the 1970s, these same airframes were the foundation for China's early warning program, a chain of influence stretching from Wichita to Vladivostok to Beijing. And in post-war Europe, German engineers who had studied the B-29 systems found themselves rebuilding new air forces under NATO or Soviet supervision. The very men who once analyzed its blueprints now applied its lessons to the Lockheed F-104 Dassault Mirage and MiG-21, fighters born from the same logic of integration, altitude, and speed. Industrial legacy. Technically, the B-29 also revolutionized how aircraft were built. Its semi-monocoque fuselage, integrated electrical system, and modular subassemblies became standard manufacturing practice. Boeing's engineers used the same production philosophy to design the Model 367-80 prototype, which evolved into the 707 jetliner, the foundation of modern commercial aviation. Thus, the superfortress's legacy divided into 2 branches: the military line that led to the B-52, and the civilian line that led to global air travel. Both shared the same skeleton: pressurized fuselages, hydraulic control redundancy, and long-range endurance. In a real sense, every passenger jet that crosses the Atlantic today carries within it the ghost of the B-29. The sky it ruled. By the time the last active-duty B-29s retired in 1960, they had logged over 125,000 sorties, spanned 3 wars and trained 2 generations of pilots. Yet the bomber's true conquest was conceptual. It had taught humanity that the sky was not a boundary but a battle space, an arena governed by altitude, velocity, and system coherence. In the archives of the U.S. Air Force Museum at Wright-Patterson AFB, the surviving airframe boxcar stands in silent contrast to its Soviet twin at Menino Air Museum, near Moscow. The two machines, identical in form, divided by ideology, represent the start and symmetry of the Cold War. Both trace their lineage to the same blueprints, both embody the same engineering truth, that dominance begins not with weapons but with understanding. Epilogue. In 1944, when German engineers first unrolled the microfilmed schematics of the B-29, they recognized its genius instantly. They saw what it meant but could not build it. A year later, Soviet engineers received the same revelation and turned it into steel and sky. The Americans, meanwhile, had already moved on, turning the B-29 systems into an entire doctrine of global reach. 3 nations, 1 machine, and a single through line. Whoever masters integration rules the air. From the shattered laboratories of Dessau to the tundra runways of Kazan, from the atomic dawn over Japan to the contrails of SAC bombers over the Arctic, the B-29's shadow defined the second half of the 20th century. It began as a blueprint. It ended as an empire of altitude,